Hello everyone, welcome back. This is the last section of this chapter. This is Dr. Rhonda Kofelt. And in this section of our acid and base chapter, we're going to look at the percent ionizations of weak acids. Remember, they're much less than a strong acid. The pH of a mixture of weak acids, finding the OH minus and the pH of a strong base solution, and then finding the OH minus and the pH of a weak base solution. So we've got quite a few things going on in this section. So increasing the initial concentration of acid results in an increased H3O plus at equilibrium. That makes sense, okay? Increasing the initial concentration of acids results in decreased percent ionization. This means because you've increased the H3O plus concentration, it's going to be slower than the increase in the acid concentration. Okay, so because always you have whatever you've got for the H3O plus, whatever's ionized at equilibrium divided by the initial times 100 gives you that percent ionization. So if we want to find the percent ionization, we need to know the initial concentration of the acid, and then we need to be able to write the hydrolysis of that acid. So you've got you're finding the percent ionization. You've got 2.5 molar HNO2, which is a weak acid. All right, so you have a 2.5 molar to start with. Again, we're 1 to 1 to 1. Okay, so we start out with 0 ionization first. We're going to go down X on the reactants and up X on the products. So we end up with 2.5 minus X, X, and X. And if you look up the Ka for this, 4.6 times 10 to the minus 4. Okay, and we're going to call that small. Okay. We're going to call that small so that we can use approximation in this one. So, and it is small compared to 2.5, okay? 0.0004 is very small compared to 2.5. All right, so we've got our ice table set up. So the Ka for this we said is 4.6 times 10 to the minus 4. And that's going to be equal to our usual suspects, H3O plus times, 2 minus, divided by HNO2, which is our acid. So 4.6 times 10 to the minus 4 is equal to x times x, or x squared, divided by 2.5 minus x, and we said that we think we can use the approximation because 0.0004 is so much smaller than 2.5. So 4.6 times 10 to the minus 4 times 2.5 equals x squared. Step 4. Take the square root. So these two multiplied together is 0.00115. And then we're going to take the square root of both of those. Okay. And x is going to be 0.034 molar. So that's the hydronium ion concentration, right? That was x. And so to get the percent ionization, we've got the H3O plus divided by the HNO2. So that's 0.034 molar divided by 2.5 molar times 100. And that is 1.4% ionization. So again, we're using these same skills just to figure out what the H3O plus was. It could have just told us what the pH was or something too. And I mean, we could have figured it out that way. So that's why I give you that pH square, because everything is all, there's more than one way to do this. So, but 1.4% ionization is what you should get on there. And there's your practice. We said you can usually just ignore the concentration of the H3O plus because it's just not enough to shift equilibrium or really impact it at all. But if you put some other type of weak acid with it, then it could have an effect. And so when we mix weak acids together, it could have some type of impact on that pH. And so I'm just kind of showing you this because our first impulse is to do a lot of calculating and make this a lot more difficult than it is. So that's why I wanted to show you an example of these. All right, we're mixing. We've got 0.3 molar HF, okay, and 0.1 molar HClO. All right, so there are three things in this solution that could be impacting what's going on here. We've got the autoionization of water, which is 10 to the minus 14. Tiny, tiny, tiny. It's not going to do anything, okay? Then we've got the HClO that is 10 to the minus 8, okay? And then we've got HF, which is 10 to the minus 4. The 10 to the minus 4 is so much larger than the other two that it's really going to be the only thing that impacts it. So when we do the ice table, we're just going to look at the HF because the impact from the HClO is going to be 10,000 times less than the impact of the HF, which means nothing, okay? And so because of that, you can ignore that and just use the HF. And the Ka for the HF is 6.8 times 10 to the minus 4. And we're just going to do H3O plus and F minus. And what I'm telling you is you look at this, and if this one is so much larger, then none of the rest of them are going to impact anything. Your entire effect is going to be from the HF because they're already, all of them are weak anyway, okay? So instead of worrying about all those other things, you just have to worry about that HF because of its large impact. All right, and then that was HF, and then Ka, which equals 6.8 times 10 to the minus 4 equals x times x divided by 0.300 minus x, okay, which is small enough for approximation. So 6.8 times 10 to the minus 4 times 0.3 equals x squared. The square root of 2.04 times 10 to the minus 4 is those two together, is equal to the square root of x squared. X equals 1.4 times 10 to the minus 2. And I'll tell you, if you're looking at answers in the back of the book says 1.4 times 10 to the minus 3, but I've worked this a bunch of times, and it's not. Okay, so then it's wanting to know the pH of this mixture, right? And so we're going to take the negative log of 1.4 times 10 to the minus 2, and that it gives us the pH, and the pH is 1.85. All right, so this has worked exactly the way we were doing the other things. The only point here is when you have a mixture, you look at them, and if there's a big difference between the KAs, then you only have to use the one with the KA that has the biggest impact. And there is your it wants you, on this one it wants you to find the concentration of the mixture. All right, so just like the Ka, if it was greater than 1, then it was going to be a strong acid. If the Kb is greater than 1, it's going to be a strong acid. If you have an ionic base like sodium hydroxide and things like that, everything's going to dissociate into ions, so it's going to make a strong electrolyte. If you have a strong monohydroxy, just one OH base, then the concentration is going to be this of the OH at equilibrium is going to be the same as the original concentration of the base. All of this is just like the acid worked, okay? It's just with bases. If you want to find the pH of that solution, typically you'll find the pOH. So take the negative log of your hydroxide concentration, and then you can subtract that from 14, and that will give you the pH. For a strong polyhydroxyl, then it has to be equal to the number of hydroxides in there. So like, for example, calcium hydroxide has 2 hydroxides, okay? And so if you have 0.1 molar calcium CaOH2, then the OH is going to be 0.2 molar because it's 2 times, it's going to be 2 times like CaOH2, because you're going to get a Ca2 plus and 2 OHs. Okay, so that's why that's the case. All right. Okay, so let's work some, and maybe it'll make more sense. All right, what are the OH minus concentrations and pH of these solutions? So in A, you've got 0.225 molar KOH. Now, how do you tell strong bases? Strong bases are your groups 1A and 2A, so that's the first 2 columns on the periodic table that are attached to an OH. You can very safely assume those are strong, and then everything else is going to be weak. All right, so you've got KOH, which is strong. So when you put you have a solution of KOH, then that means that since it's strong, everything is going to ionize into K plus and OH minus. So the OH minus is also going to be equal to 0.225 molar. Now, so that's the concentration because it's strong. If you want to know what the pH is, you can do it one of 2 ways. You could do it with, you could say, remember when we did this, the Kw divided by the OH is going to give you the H3O plus, okay? Or, so if you do it that way, then 1 times 10 to the minus 14 divided by 0.225 is going to give you, let's see where I got it, 4.44 times 10 to the minus 14, okay? And then, so the pH will be the negative log of that. Sorry. 4.44 times 10 to the minus 14. And so the pH will equal 13.35. So I did the KW rule here to get the H3O plus concentration. All right, so that's one way I could have done it. The other way is I could have just done the negative log of that. Okay, so that's way one. Way two, I could have taken the negative log of the OH minus, or the negative log of 0.225, and that should have given me 0.65, okay? And then to get, so that's the POH, right? So then 14 minus the POH, look at your square, would give me 13.35 if I did that right in my head, okay? Which was equal to pH. So you could have done it this way or this way, either one. The second example, I'm going to erase this so I can have room to do the second one, okay? So if I erased it before you wrote it down, you can go back and get it, okay? All right, so in this one, we're doing strontium, which has got two OHs. And it's also strong because it's in group 1A or 2A, to give you strontium 2 plus 2 OH minuses. So remember, in this one, you've got to remember that your OH minus is going to be equal to 2 times whatever that original concentration was, 0.0015 molar. 0015 molar. Okay, so that's equal to 0.0030 molar. And then again, you can work it either way. So I'm going to take the negative log of that, of 0.0030, which is going to be the POH. And that's going to give me 2.52, and then 14 minus 2.52 should give me 11.48 as the pH. Remember, you could have done it the other way with the KW. I just did it this way. Because I don't care how you do it, as long as you're doing it one of the ways to get it right, okay? So how you do it is really up to you. All right, so weak bases. See, that one was a strong one. This is as weak. All right, most of these, remember, we're just putting them in water and seeing what happens. In the weak bases, just like the acids before, only a small fraction of the molecule is going to accept the hydrogen ions this time and form those conjugates. So it's going to be a weak electrolyte. Ammonia is one you see a lot, NH3. And then an amine means it has nitrogens in it. That's an organic base, carbonates, things like that, okay? Really, the only one we see that's not organic typically is the ammonia. It's kind of like the poster child there. Finding the pH of that is the same as we did before using the ICE table, that if you recall. So what we do is we have the base ionization constant Kb, and so these Kb's, they're the same relationship as you saw before. If you have the Ka, if you divide 1 times 10 to the minus 14 by the Ka, that'll give you the Kb. All right, because acid and base, they're just the opposite in aqueous solution. And so if I have a base plus water, it's going to ionize and accept the hydrogen and form an OH minus because it's a base. And the Kb will be equal to the BH plus times the OH minus divided by the original concentration of the base. This is exactly like the acids. It's just you use a base and a Kb instead of a Ka. All right, so again, we're 1 to 1 to 1. Okay, so the NH3 has accepted a proton, so it is now NH4 plus. Your original concentration is 0.1 solution of your ammonia. You have 0 starting out because you hadn't made anything yet. They're all 1 to 1, so this one will go down X and these two will go up X. When you get done, you're going to have 0.1 minus X, X, and X. The KB for this is 1.76 times 10 to the minus 5. That's pretty small, so I'm going to say it's small. So our KB, which is equal to 1.76 times 10 to the minus 5, is equal to the NH4 plus times the OH minus divided by the NH3. All right. So 1.76 times 10 to the minus 5 is equal to X times X divided by 0.1 minus X, which is small enough for approximation. So 1.76 times 10 to the minus 5 times 0.1 is equal to X squared. See how familiar this is? All right. So that's 1.76 times 10 to the minus 6 is equal to X squared. We're going to take the square root of both those. So X is going to be equal to 1.33 times 10 to the minus third, which is our hydroxide concentration, because remember, hydroxide is telling us how basic it is. Okay, and again, you can do it either way you want to. You can either do it with the kW, you can divide that by kW and get your hydronium ion concentration. So I'll do it that way this time. So 1 times 10 to the minus 14 divided by 1.33 times 10 to the minus 3 is going to be equal your H3O plus, right? And so that's going to give us 7.52 times 10 to the minus 3. No, minus 12, sorry. All right, and so the pH is going to be the negative log of the H3O plus, which is the negative log of 7.52 times 10 to the minus 12. And so the pH is 11.12. Okay, you could have done it by taking the negative log of the OH of 1.33 times 10 to the minus 3. Oop. So that would have given you the POH oops, 14 minus, sorry, I didn't have it done that way, so 2.88, right? And then the pH is equal to 14 minus 2.88. pH is 11.12. So this is the second way. So you can do them either way. Once you get X, then you can do it the first way using the kW, or you can do it the second way, getting the POH and then subtracting it from 14. I honestly do it this way usually because it's just easier. It's less exponents. Okay? So that's how you do the hydroxides and get the pH. You just have to remember you're getting a POH and you've got to convert it to a pH. The last part of this is we don't do a lot with Lewis acids and bases because you're going to do that in organic if you go farther. But remember I told you that instead of looking at protons, Lewis acid base theory looks at electron pairs. And so when in organic reactions, you're going to see that there's a lot of transferring of electrons in order to make and break bonds. So if you have a lone pair, it can go to a bond. If you have a bond, it can go to a lone pair. What that means is you don't have to have hydrogen atoms to be an acid. You can be a Lewis acid without having hydrogen atoms. The electron donor in this case is the base, and the electron acceptor is the Lewis acid. Okay, and so the electron donor we call a nucleophile, okay, because that's where the electron rich part of this comes from. And then the electrophile is the electron acceptor because it loves electrons. So the electron donor loves the nucleus, and the electron acceptor loves the electrons. And so the Lewis base donates a pair of electrons to the acid. Okay, so if you've got H3N and you've got a pair of electrons there, okay, it donates them to that and creates a bond. So that's what we're talking about. This Lewis acid and base nucleophilic attacks or electrophilic attacks, you'll see that. This is called an adduct once it's made that molecule. Okay. Arrhenius and Bronsted-Lowry acid-base reactions are also Lewis, okay, but all Lewis are not Bronsted-Lowry or Arrhenius. And so again, it's basically what you're doing is you are attacking electron pairs and you're causing them to move. And so as you're doing that, you're creating a molecule. And basically, for me, organic wasn't very difficult. I really enjoyed it because I could tell what it was going to do. If you have a lone pair right there, okay, that lone pair is just going to share with that, and that creates a bond. And that's all we're doing with these Lewis acid-base reactions is we are moving things around and causing them to bond to each other. And that's the end. So on the Lewis acids and bases, just make sure you know what they are, which one's a donor, which one's an acceptor, okay?